Hi, I'm Peg Jones. I'm a materials engineer with a large automotive company.
And I'm Laura Moore. I teach material science at a public high school.
And Laura's been brave enough to test drive the curriculum modules we're going to show you today in this brief video. The goal of our video today is to give you an overview of the lightweight design modules that we've developed. These involve in-class videos, teacher resources such as planning guides and assessment guides, alignment to curriculum standards, experimental procedures to share with your students, and some short videos. All of that will be available through the ASM Materials Education Foundation website at no cost to you, and you'll be able to download it. So I'm going to explain a little bit about what is lightweight design. These curriculum modules were funded by a research consortium called LIFT, which stands for Lightweight Innovations for Tomorrow, and we're part of their workforce development initiatives. So lightweight design is simply the engineering approach of trying to make the lightest possible part to get the job done. And in a way, we're catching up to what Mother Nature has always been doing. You may know that bird bones are hollow. And this is an example of a bird bone. You can see it's a really unusual shape. It's not a square, it's not a circle. So nature has put the bone material only where it's needed for function. And inside the bone, there's a strut system that's very irregular. Again, nature is putting material, it's putting mass only where it's needed for the function. The density of that bone tissue is varying depending on where it's placed. So the science of lightweight design is about the shape of the component and also the materials from which it's made. When I talked to Laura's students about where lightweight design mattered in their daily lives, we said to them, tell us about an object where the weight of the object matters to you. And one student in her class was a tuba player, so that was an obvious example of where the weight of the tuba would make a big difference. Other examples that they gave were sporting equipment and the electronics that they haul around every day. One of the videos that we'll be offering you for classroom discussion is based on a very athletic young lady who's a bone cancer survivor, and she has a lower leg prosthesis. So she'll be describing how the mass of her prosthesis affects what she's able to do. She recently completed an amazing journey running, biking, and swimming from Seattle to San Diego to raise awareness for prosthetic access. A second video that we'll be offering you online for free is created by her prostheticist, which is a hard word to pronounce. Her prostheticist was a mechanical engineer who wanted to help people, and she actually built Nicole's leg. So she's going to be talking about the engineering choices and the materials choices that go into that kind of a prosthetic. So in the past 10 years, you may have run into some commercial discussion of lightweighting, particularly in the automotive side, because the more weight that we can take out of your car, the better fuel economy you're going to have, the lower the CO2 emissions for the car. And it's also green, because if we don't have to create the material to build the part in the first place, we're polluting less and we're using less of the raw material. So what we tried to do was pick an example where engineers are working on advanced materials and processes to create the lightest possible component. And I wanted to pick something that everybody could relate to. As an engineering student, I would be assigned homework problems like what material would make a good tappet. Well, my Barbies didn't have tappets, so I had a triple hard homework. I had to figure out what a tappet was, what it did, and then what should you make it out of. So we tried to pick an example that everybody could relate to. And what we picked was the B-pillar. And most people don't have a clue what a B-pillar is. And one of the teachers who worked with us on developing this actually thought it should be shaped like the letter B. The B-pillar is the metal between your driver's door and the passenger's door, the rear seat door, and it protects you in a side crash. So you might hear the IIHS crash test ratings for new models coming out. So IIHS sets up their impact tests with a fixed mass moving at a fixed speed into the side of a car. And they measure the success by how far that B-pillar, how far that strip of metal deflects across the driver's seat. So the distance that it intrudes into the driver's position is what gives you the good, fair, poor ratings for crash tests. So we suggest when you present these activities to your students that you would show them a crash test video so that they can relate directly to that. So we picked a B pillar so that everybody could relate to it because we all care about safety of our families. And the only problem with picking the B pillar is that in real life, B pillars are actually very complicated shapes. Many B pillars in weight-conscious design are layered structures that get welded together. And I found an example that I'd like to share with you where you can see the individual pieces that get welded together have variable thickness. And it turns out that once they're welded together, depending on where you are along the height of that B pillar, you're protected by the equivalent of 15 sheets of copy paper or 82 sheets of copy paper in terms of the steel thickness. We're also varying the strength of the steel that goes into each of those little components. So we had to figure out how to simplify this problem so that you can bring it to your classroom. And we picked a simple shape. We picked just a rectangular beam. There are actually fairly straightforward formulas to predict how far the beam will deflect. Because remember, in the B pillar example, the score is based on how far the B pillar deflects after it's crashed with a certain amount of energy. The lab activities use equations relating the beam deflection to beam geometry, material, and load applied. Students will use these equations as part of their engineering design process. Let's look at the equations related to the stiffness of a beam, the shape of the beam, and the material from which it was made. You may be familiar with the spring constant from physics, usually symbolized by the letter K. A higher spring constant means it takes more force to stretch a spring a certain distance. In our labs, we're going to clamp one end of a rectangular beam to a table, like a diving board, and have students measure how far the beam moves down as they incrementally increase the force on the end of the beam. The deflection, or how far the beam moves down, is y in our equation, and the applied force is F. The shape of the beam comes into play in the red color variables I, the area moment of inertia, and L, the length of the beam. I'll explain the moment of inertia in a minute. The material choice is the blue variable, E, the modulus of the material. The superscript 3 after the length just means that we are multiplying the length of the beam times itself 3 times, or cubing it. We need to rearrange the equation to be able to predict the deflection. Students will be determining the value of the elastic modulus in Lab 2 and varying the beam dimensions in Labs 1 and 4. In all of the labs, we'll be measuring how the beam deflection increases as we add mass to the end of the beam. Starting from our original equation on the right, we just multiply the right side by y, the deflection, and divide the left side by the modulus and shape variables. Next, let's plug in the width and height of the beam for the area moment of inertia, I. The cross-sectional area of the beam affects its stiffness, and we represent that effect using the area moment of inertia. For our rectangular beams, the area moment of inertia is 1/12 the base dimension of the beam, or width, times the height of the beam cubed. There are similar formulas for other beam shapes, such as the cylindrical beam shown here. Additional formulas are given in the teacher training package. Finally, plugging the beam base and height into the equation for beam deflection to replace I, we find the equation used in the student worksheets to predict the beam deflection. That equation is shown here. So, to be able to get the kids started in thinking about how rectangular beams deflect, you can do something as simple as take a meter stick and put it on the edge of the table. Notice how much length is sticking out, that's your length variable, and then you can push on it and see how much you have to push to deflect the end of the beam. So I'm calling this diving board orientation. Then if you flip the beam 90 degrees, and I'll show the metric, because you guys are science teachers. If I try to deflect this, I can barely deflect it at all downward. And that's because of the geometry effect on the deflection of the beam. So this is just a very simple experiment, and the students can do it, and you can vary the length of the beam by how much is protruding over the edge of the table. So no cost, no fuss, but it gets you past some of that initial reaction to the math. So Laura was brave enough to test drive these labs as we developed them. So I'd like to invite her back in to talk about how she aligned it with the curriculum and the NGSS standards and how she actually presented them to her students.
Thank you so much for having me. It's been such a pleasure to be able to pilot these labs as part of the ASM work. So One of the beautiful parts for me as a teacher in the classroom is that these are directly aligned with the NGSS standards, specifically in the engineering standards themselves. There are 4 labs, each have an optional crash test that goes with them, which of course are the students' favorite part. And the first lab focuses on just the shape effects of having the beam in different shapes. The second lab focuses on the material effects. If we start changing the materials, what impact does that have on the beam? And the third and fourth integrate both shape and material, and even offer the students a little bit of a chance to be creative in the materials that they use. In this video, we're going to show you the experimental setups for labs 1 and 2 and the crash test options. There's a short video available for each of the labs if you want more details. Labs 2 through 4 use the same test setup to measure the beam deflection. The purpose of Lab 1 is to demonstrate the difference that shape makes in the beams. Students are going to use folded tag board or manila envelopes in order to look at 2 different shape beams, one that's been folded wide and one that's tall and thin. This also offers an opportunity to go between the solid B-pillar formation and the rectangular shape we need the beams to be for the labs to be effective. Students can stack materials on these beams to see how much mass the beams will hold before they collapse, showing the difference that shape makes between the 2. Another option is to poke a hole in the beam itself. You can distribute the weight with a simple washer and hang a cup and start adding water as your mass to see how much water the beam will hold before it collapses.
Ooh, we need more water. Nope, we got it. Ooh, and it didn't spill, even better.
Even better. Based on their experience flexing the meter stick, students are asked to predict which beam will support more weight before it collapses. You could use coins, washers, the water, all sorts of options to test the beam itself. Another option for Lab 1 is to ask students, if there were a crash, would your doors be wide open, or would there be some support offered to the B-pillar through the doors of the car? So you can sandwich the beam between 2 objects, dictionaries or books, bricks if you've got them, and go ahead and add weight and see if there's a difference between the B-pillar collapse with doors open versus doors closed. I think you'll find that students find the amount of weight that they can put on the pillars pretty impressive.
So the weights that we're using here are actually cut up pieces of tin, so it's quite heavy. And I'm trying to center them along the center line of the beam as best I can. The other way to do this is to support the beam as we did with the cup hanging below, and then add the supports to the side. And so you can hang a fairly large container and use a lot of sand or water to add quite a bit of mass. So I'm going to see if I can start stacking tin nuggets. Not very well. So we can mass these tin nuggets, but there's probably close to half a kilogram on there now, and it's still hanging in there, so no collapse. So this lab was designed to bridge the gap between the B-pillar, which is constructed of sheet metal, and the engineering test requirement, which was the crash test with the doors closed, and then the work that we'll be doing to engineer a lightweight beam out of solid rectangular shapes. So I've bent the beam, but it hasn't completely collapsed.
Lab 2 focuses on the difference that material choice makes in the beams. The beams can be made of anything from Rice Krispie treats to Portland cement, wood, or in this case, we've used different kinds of insulation purchased from a hardware store. It's important to cut the beams in the same shape and dimensions so that we're only changing the material, not the size or not the shape of the beam. In this case, we've hung weight or mass from the end of the beam. We're making sure that we hold or hang that mass from at the same distance for each beam, and each beam, when tested, will be off of or hanging over the table at about the same distance to make sure that we are really testing the material. Then students can slowly add water and see how much mass this beam will take before it's deflected, and how far of a deflection is acceptable.
So to make the math part of this work, the beam can only deflect a small amount. So we suggest figuring out the load at which the end of the beam deflects about 1 centimeter, maybe 2 at the most. If you get too much curvature, you're going to need calculus instead of algebra. So I can see visually that we've achieved significant deflection with that beam. And actually the students will be adding the water incrementally, and then you can plot the mass of the water added versus the deflection, and the slope of that plot will actually give you the material stiffness number that you need for the beam design equations. So if we were to change this beam out and use the lower density polystyrene, it would deflect much more under the same amount of water. And we've got a good 3 centimeters, 4 centimeters of water in our bottle. So to change our beam samples, we just have to pull the hook through sample number 1 and stab it through sample number 2 at the same distance from the end, which you can have the students pre-mark for consistency. We've added a paint stir stick to try to keep the beams from being crushed by the clamp. That's the only reason to have the stir stick involved. Okay, and you can see how quick this is to do with the bar clamp. It'll work with a C-clamp as well. And again, we want to try to keep the same overhanging length of unsupported beam for all the tests. So that's something that the students will record in their worksheet. Okay, that's pretty good. I'm afraid if I hang this from the white, it may break, but we'll see. Maybe it'll just deflect a lot. No, that's breaking. So you can see there's a real difference between the two materials. And again, this is just straight from the hardware store and cut into bars of the same size.
Labs 3 and 4 use the same concept to test deflection of the beam, but give students a little more option in terms of how they're going to test. For instance, Lab 3 includes a stressed skin deposit, composite, where students add tape to one side of the beam in order to reinforce the beam's strength. For Lab 4, students get a chance to freestyle a bit and see if they can create the strongest but lightest beam they can. They could add rebar, for instance, in kebab sticks. They could do more stressed skin composites, or there are several options depending on what you're willing to let them make the beam from.
So in the stress skin composite lab in Lab 3, we can vary the type of tape and the amount of tape, because the more tape that you put on here, the heavier your beam will be. And we can also bring in the cost factor of the tape to really make it a more true-to-life engineering exercise. And stress skin composites are what is used in aerospace design. The skin on the wings takes a lot of the stress. You'll also find it in a banana. And if you're not particularly handy and you don't have a bandsaw, so you don't want to cut up the insulation board, lasagna noodles work with the stress skin composite as well. Some of our examples that we were playing with of beams that we fabricated are straight Portland cement. This is very brittle, so you're not going to do a good flexion test on this, but you can crash test it. And in this sample, we've stirred in expanded polystyrene beads to reduce the mass of the Portland cement. And that's actually used to reduce the mass of cement. This was an example where we tried to keep the same geometry of the folded cardstock from Lab 1, and then we inserted spray foam insulation. And that worked fairly well. With different types of spray foam insulation, you can get different densities. And we were able to measure an effect on the slope of the deflection load curve depending on the foam density. This was a fairly expensive one that we made out of Uricast resin. It's extremely stiff and fairly heavy. So even though it's a polymer, it's quite heavy. I'm into found materials for lab samples. I know you guys are scroungers. Paper towel roll, piece of duct tape, my spray foam insulation. I can make a round beam. Another trick that we found is these silicone ice cube trays. You can make concrete beams in this and also polymer or Uricast resin samples in this. And if you are teaching material science and you're melting tin, you can actually make metal bars in these molds as well by pouring your tin into them. So those are some of the fun experiments that we've tried with this lab.
By the time students get to Lab 4, they're actually designing their own lab. So they're taking the materials and the shape into consideration to create a beam that they think will be the strongest and stand up the best. I have a competition against the classmates, and the students are gung-ho. This is a direct, absolute concrete, get it? Combination with the NGSS standards and students being able to design and critique their engineering practices.
As I mentioned earlier, my first experience testing beams and bending was actually working with Rice Krispie treats with 5th graders. And one thing that I didn't think about when we were hanging the pea gravel from my Super Rice Krispies was where the girls' feet would be. And it turned out that they wanted to be right under where all that pea gravel was going to fall. So as we designed these crash test approaches, safety was my first priority. We also wanted to make sure that we could accommodate a range of beam strengths, because these folded cardstock beams from Lab 1 are quite fragile. So for Lab 1, we've devised a simple pendulum drop test. Whoops. And you can vary the mass of the water in the bottle, and you can vary the height from which you drop it. So you can create a fixed energy crash test condition, or you can determine by increasing energies whose beam performs the best. The students can also film the deflection if they have a high-speed camera in their cell phone. So we've included a quadrille piece of paper inside an old cardboard box as a way to provide you a measuring device. And we figured that most everybody has a ring stand somewhere in their school. So we simply snug the beam up against the ring stand support. I have duct tape wrapped bricks behind here to make sure that nothing moves. From a safety point of view, you just want to make sure that nobody's in the path of the bottle. So we're going to adjust this. I've got an aim line written on my beam, and I want to try to hit that pretty much dead center. So we can determine what our crash test criteria are. We could say we're going to drop from a fixed distance above the table, or just come to 90 degrees. I'm going to start out a little bit lower because I'm not sure how strong this particular beam is going to be. So I want to try to square him up and let her rip. Well, that didn't do much damage. Okay, so we definitely had a crash event. We can look at the permanent deflection on the beam, and we can relate that fairly easily back to the IIHS crash test. Okay, so crash test method number 2 is devised by Scott Spoler, who teaches down in Ohio. And Scott is a shop teacher, an industrial technology teacher, so he drilled holes in a PVC pipe. You could also put holes in a heavy cardboard tube, like from gift wrap. We have a pin that goes through the holes. We can vary the energy of our impact event by varying the height from which we drop a mass. And we can also vary the mass I have 3 different masses here. These are just 1-inch bar stock of steel, cut so that they fit down the inside of my tube. We would normally attach the tube to something in the classroom so the weight of the tube is not resting on our sample. But for our demonstration purposes, we're going to start with a big mass. This is 238 grams. We have our pin at the 4th height position here, and you physics teachers will know how to convert this from potential to kinetic energy. Fire in the hole, pull the pin. Okay, so we have failed a crash test with our beam, because obviously that didn't protect the people inside. So we can back off on the mass and run it on the other half of this beam. And you can see how simple this is. Sorry, it's a stretch to get that up there. Okay, ready, set, go. Okay, so we've dented our beam, but we haven't broken it. So this is a real versatile piece of equipment. You can use it to break concrete samples as well. So that's crash test idea number 2. I like it because you can see if the beam had bent but not broken. You can get a measurement underneath. And it's also very difficult to get a body part underneath the crash zone. So this is crash test idea number 3 using household ladder, string, and 2 pieces of broken paver blocks scrounged from Home Depot for free and wrapped in duct tape so they don't hurt the floor. This has actually been proposed as a good bounding exercise for elementary school kids. If you have to guess how much energy it's going to take to break your beam, you could try bouncing different balls off of your beam to get an idea of what kind of mass is required. We set this up with our lasagna noodle, and this is a golf ball in a Ziploc bag wrapped with twine, so it's not a very elegant experiment. So for a fixed energy crash condition, you can set a fixed mass and drop it from a fixed height simply by laying a meter stick across your steps of your ladder and then lining the weight up with that meter stick so you know the height. Or you can vary the energy and determine the winner based on which beam absorbs the most energy without actually touching the floor at the end of the crash test event, because we're going to define touching the floor as a failure. Laura, you want to let her rip?
I'm ready. In 3, 2, 1.
Okay, so our golf ball from that height cracked our lasagna noodle, but I had reinforced the bottom with duct tape. So even though the lasagna cracked, it didn't touch the floor. So our lasagna noodle with duct tape would have been a winner based on the test criteria that we defined. We can run this again with one of the foam beams and a larger mass to demonstrate how it works with this more substantial specimen. So we've just tied some zip ties around a hand weight and we're hanging it from the ladder. I've got one of our pink foam insulation beams supported between our paver blocks. And we're going to try to do this with variable crash energy by raising the weight to successively higher starting points. Laura, you want to let it go with the first one?
Here we go.
Oh, so that was too high. We need less weight. But that was a rather spectacular failure. We managed to break it in 3 places. Okay, so we'll try from a lower height and reduce the energy. All right, let's see if it can take a lower intensity hit. Okay, so you can see, physics teachers, how you can vary the energy very simply with this. Okay, so you might remember in lab number 4, the students are able to design their own beams by carving out supporting material where they think it's not worth the mass in terms of contributing to the stiffness, and they can add reinforcements. Here we've used bamboo skewers as our reinforcements, as though they were rebar. So we're going to see how much this beam can take. And this is our lower strength styrofoam, the white styrofoam insulation. Okay, Laura, let her rip. Let's see what we got. All right, we'll have to try again. Raise it up. Okay, this is one tough assembly. Ready? Okay, unscathed. 3 drops. from as high as we can go. So I think, Laura, when you ran this lab with your students, you were having trouble getting things to break because they'd done such an amazing job reinforcing them.
We were, but they did start to lose track of the light weighting issue. So you do want to remind students that they do need to keep in mind the mass of their beam overall.
If we've piqued your interest in trying to do these experiments demonstrating lightweight design principles with your students, just as a reminder, all of the materials, including the teacher resources, student handouts, assessment guides, and some short videos, will be available at no charge to you through the ASM Materials Education Foundation website. And that's courtesy of ASM and the LIFT Consortium, who has sponsored this.
LIFT is also developing additional teacher resources, and you can access them at the LIFT Learning Hub. The website is on the screen. If you're interested in even more ideas, then we encourage you to look into the ASM Foundation-sponsored teacher materials camps. They're week-long camps across the country that are all sorts of good fun. Please consider attending one of these if you're interested in low-cost, fun labs to pique your students' interests as well.
So I'm Peg Jones.
I'm Laura Moore.
Thanks for watching our video, and thanks very much for all you do for your students each and every day.